another type of frictional force that we haven't considered yet that is very important when designing moving objects or analyzing the motion of objects in a real world setting, not in a vacuum. So one which we take wind resistance or air resistance into consideration. You've all probably experienced wind resistance in some form or another. Maybe when you're driving down the road and you stick your hand out the window a little bit, you feel some wind resistance there. You know that a piece of paper would take longer to fall to the ground than a rock because the wind resistance on the paper is stronger than it is on the rock. And so this wind resistance is what we call a drag force. So it's drag. So when if we have like a bobsled here, this bobsled has been designed to reduce as much of this drag force as possible. Also, we have an airplane. When airplanes are designed, they're put in a wind tunnel, and you can put some colored air. So you put some sort of coloring in the air, and then you'd send a jet stream over this plane. You can look at how the air flows over this plane to determine how aerodynamic it is before you actually build a full scale plane. Even birds fly in a V shape, and this is because it is more aerodynamic to fly in a shape which is like this than it would be if they were just if they were all in a line like this. It would be much less aerodynamic, and so this occurs in nature. Birds know about it, and also we've extrapolated this to designing things that move on Earth. So, what is this drag force? This drag force is, we'll call it FD, and this is equal to 1/2 times the coefficient of drag times the density of the fluid times the cross-sectional area times the speed squared. This is what the drag force is. And this is just like a frictional force. It always resists motion. So if I have a velocity, if my velocity is this way for some object, then I will have the drag force would be opposing it. And so I'd have my drag force like this. Okay. And let's go through what each of these mean. The drag coefficient, CD, this is the drag coefficient. It is a function of the shape of the object. So it describes the shape. When air flows over an object, there's a couple ways in which it could flow around it. Let's say I have a wall essentially here, or I have something like this V over here. So when air flows around these, so let's say I have air flowing in like this, air flowing in like this, then this one, it hits here and it has to just like stop and then go around, right? And all of these have to do the same thing. They have to stop and go around. This one can kind of hit and then go off in this direction. It doesn't have to change it changes velocity quite as much. The air particle here has to change its velocity by like a 90-degree angle, then go around. Has to change it quite a bit. This one doesn't have to change it nearly as much. And so we know a change in velocity is an acceleration. The rate of change of this is a force. And so we have basically these different shapes have different drag forces because of how they change the air flowing over it. And so actually we have here, this is this drag coefficient. This is a table of the drag coefficient here, CD. And we usually just have a table. This is measured experimentally, very much like your coefficient of friction, which we had. This is kind of like mu that we had before. If we have, you see like a sphere it hits and kind of goes around like this, the drag coefficient is 0.47. A half sphere is 0.42. It's a little bit less because the air is then freed up over there. A cone is 0.5. A cube is 1.05. It hits it, then has to go around. An angled cube, so if I simply take this cube and I rotate it, then the drag coefficient goes down from 1.05 to 0.8. So a little bit different. We see a long cylinder, a short cylinder, a streamlined body, one in which it has been aerodynamically designed so that the air flows in and then goes around like this, is very, very low, 0.04. Half of a streamlined body, 0.09. And there's more to just when it hits, and also when air flows over the back of something, it has a tendency sometimes to curl like this and become turbulent. If you have a streamlined body, it allows this not only to separate very slowly, but to come back together very slowly, so that way you don't get this turbulent flow behind. That's why you get a streamlined body has such low drag coefficient. Anyways, so drag coefficient it describes the shape. This density here, we'll talk about this a lot more in later chapters, but this is the density. This is the Greek letter rho, R-H-O, and it is equal to the density of the fluid, the fluid that the object is flowing through. And what density is mass, how much mass there is divided by the volume. Like I said, we'll define this later chapters in fluid mechanics, but for now you'll just be given the density of the fluid. A is the cross-sectional area. So if I have let's go back to these and look at their cross-sectional areas. If the fluid air is flowing in this direction in all of these, so flowing from left to right, then the cross-sectional area would be, I would chop it in half, and it would be this area right here, or chop this in half in this area. So we have these areas. When you chop this in half, that's your cross-sectional area. Okay, it's your widest area of it. So the area, like if I have a sphere and I chop it in half, then that cross-section area would just be a circle. If I cube and I chop it in half, that cross-sectional area would be a square, etc. So this is the cross-sectional area. And then V is your velocity, but since we square this, it really becomes the speed squared, right? So this is basically just the speed then. And the direction of the drag force will always be opposite the motion. So we see here, let's just rewrite this drag equation. The drag force is equal to 1/2 times the coefficient of drag times the density times the cross-sectional area times the speed squared. You see here, the faster we go, the greater the drag force. And so if we double the speed, then we quadruple the drag force. So if we were to make a plot of drag force versus velocity, we'd say here's the drag force, here's the velocity. Then when I have this is exponential, right? And so the graph of this is going to look something like that, right? So as the speed increases, the drag force increases exponentially, okay? So let's take into consideration an object and free fall for a minute. So let's say we have this box here, and it is falling down. So let's say that it falls from rest. But now we're not neglecting wind resistance. But let's say I have a weight acting down here. And then my force is in the y direction. Give a sign convention here. Sum of forces in the y direction will be equal to negative mg, which will be equal to mass times acceleration in the y. And so we can see here, acceleration in the y direction will be equal to negative g. And then it'll speed up, right? And after it speeds up, as it's speeding up, the drag force is getting bigger and bigger. So I would this would be when the initial velocity in the y direction is equal to 0. But then if I take into consideration a moment later, it still has a weight acting on it, but now it has a drag force acting up like this, right? And so now the sum of my forces in the y direction will be equal to mg, using the same coordinate system here. This will be Fd, the drag force, minus the weight, will be equal to the mass times the acceleration in the y direction. So my acceleration in the y direction is going to be a little bit less now, right? Downwards, because the drag force is pulling it up, right? And then as we continue going on and on and on, there's still a weight acting down, and then the drag force gets larger and larger and larger. Eventually, this drag force, the more it speeds up, the more it slows down, right? And so, the more it speeds up, the greater the drag force, and so it's not speeding up as much. Eventually, when the magnitude of the drag force is equal to the magnitude of the weight, then we could say that the acceleration in the y direction will be equal to 0, because the net force will be equal to 0. So then therefore, we will have the velocity in the y direction will be equal to a constant. It will stop speeding up. So we will have the y velocity will be a constant because the forces have balanced and the acceleration is equal to 0. This is a condition we call terminal velocity. So terminal velocity is the drag force is increased enough that it balances the weight and the object stops accelerating, so the velocity remains constant. This is what terminal velocity is. For instance, let's say that we were out skydiving, and here you're falling down like this, and so the wind is flowing over like this here. So effectively you could be a shape like this, right? If you wanted to increase your velocity, remember here the drag force is equal to 1/2 times the drag coefficient times the density times the area times the speed squared. So we could change our drag coefficient, and we also change our cross-sectional area and the drag coefficient, and you can become more streamlined, maybe a shape like this. And so then therefore reducing this one and this one, we can increase the speed, right? So then the air, instead of it flowing around you like this, flows around like this. And so you can increase the terminal velocity, your maximum velocity. You can go there. Also, if you wanted to slow down, the way that we typically would do this is to open up a parachute. So let's say you have a parachute here, something like this. Then you've now increased the cross-sectional area and you've increased the drag coefficient, and so then you're going to reduce the speed that you can fall at a constant rate. So terminal velocity is when this drag force equals the weight, and it would be the constant velocity at which you would fall at. This is what we typically refer to this as Newton's drag. There's another type of drag for objects moving very, very slow, and this follows what we call Stokes' law. So Stokes' law says that we'll call this the drag force for Stokes. So Fs is equal to 6 times pi times the radius of the object, which is moving through a fluid, times this is eta, this is the viscosity, and then times the velocity. And so this is the Greek letter eta, which is the viscosity of a fluid. Again, we'll talk about this later on. But this is a measure of the internal friction. You could think a high viscosity fluid would be syrup, and a low viscosity fluid would be water. So the greater the viscosity, kind of the slower it moves if you pour it out of a bottle. You could think of it like that. So Stokes' law. This is only for fluids which have a density much greater than air, and also for very slowly moving objects. So we would use Stokes' law. Let's say we had I don't know, a bucket filled with some syrup or something. So there's like a syrup in here, and you put a ball on top, like put a marble on top, and then let it fall through. And then we would use Stokes' law for this. Majority of the problems we do in the class are going to have to do with this Newton's drag as opposed to Stokes' law. But if we have very slow moving objects, then we have a different drag equation for them.